Welcome back everyone to another video in our Fundamentals of Structural Engineering course. In this video, we are going to talk about structural design of steel beams. We have talked earlier about the steel design of columns and the steel design in general, and we mentioned that buckling is one of the main issues that we face during the design of any steel members. We have explained earlier the process of designing columns, and we learned how to check the buckling for any steel column. However, for steel beams, it is different, because steel beams are not subject to pure compression forces. However, most of the time they are under the effect of bending moment. And as we have learned earlier, bending moment creates tension and compression in the lower and the upper chords. That's why the buckling has different modes in the beams rather than in columns. The first buckling mode that we have here is called local buckling. And as we can see here, the whole beam could be intact and it has no issues. However, only in a specific area, as you can see, there is buckling in the lower chord of the beam. This type of failure, it is called local buckling, and it depends on the slenderness of the section and the dimensions between the web and the flange and the thickness of each. We have three types of steel sections, which are compact, non-compact, and slender. Local buckling happens only in the slender sections. However, it cannot occur in non-compact or compact sections. In our FE course here, we will be dealing only with compact or non-compact sections. That's why you will never have to check for local buckling. Of course, this is during the FE exam. The second failure mode which we have for buckling is called lateral-torsional buckling. As you can see here, we have this beam. This beam is subject to vertical force, which is going to create a bending moment. Once a bending moment occurs in this beam, you will have tension forces in the lower chord, and we will have compression forces on the upper chord. This difference between tension here and compression here is going to make the beam buckle laterally between both chords, the lower and the upper chords. And that's why it is called lateral torsional buckling. And the lateral torsional buckling depends on the unbraced length. As the longer the unbraced length is, the more this beam will be vulnerable toward lateral torsional buckling. And lateral torsional buckling occurs in slender and non-compact sections. So now let's summarize what we have learned. In order to check the design of any beam, we need to check first the failure modes. In order to check the failure modes, we need to understand first what is the type of this section. It will be mentioned, of course, in the problem. You have compact sections, you have non-compact sections, and you have slender sections. If your section is compact, then there is no any buckling will occur, neither local buckling nor lateral torsional buckling. And in this case, you are going to check yield stresses directly. The second type of sections, which is non-compact sections. For non-compact sections, you don't need to check local buckling, but you need to check lateral torsional buckling first. And the third type, which is slender, which in this case you need to check both, and this case is not applicable during the FE exam. In order to design the lateral torsional buckling, we have learned that it depends on the unbraced length of the beam. Here we have a relation between the available moment or the design strength of a beam and a relation between the unbraced length. This zone is called the plastic zone, this is the unelastic, and this is the elastic zone. The higher the unbraced length, as you can see here, the lateral torsional buckling is going to occur at lower value of moment. Here, as you can see, it is going to give you a lower strength of the beam. And the lower the unbraced length, it is going to give you a higher value. Here in the plastic zone, it means that the lateral torsional buckling will not occur unless the whole section is loaded and reaches the plastic stress. And here in this stage between the plastic and between the elastic, it means that your lateral torsional buckling is going to occur in the inelastic stage. And here this is the worst case, of course, which means that the lateral torsional buckling could occur during even the elastic stage. And this case we never accept it. It has to be either here or here. So here there are two parameters, which are LP, length for plastic, and LR, length for the elastic. And this is a relation with the LB, which is the length unbraced. In order to find out which equation you need to use for the design strength, you need to find the L unbraced and compare it with the LP and LR for the section, and based on it you find out in which zone you are. If you are in the plastic zone, which means that your LB is lower than the LP, this means that the limit state of lateral torsional buckling does not apply, which means that you can apply directly in the yielding equation, which is Mn equals MP, the plastic moment, equals F yield multiplied by Zx, where Zx is the plastic section modulus, and this is you can get it from a table as you are going to see in this video. And in case if you are here in this zone, which means that LB is higher than LP and lower than LR, you are going to use this equation, which is Mn equals Cb multiplied by MP minus 0.7 F yield Sx, all multiplied by LB minus LP over LR minus LP. And of course, all of this has to be lower than MP, and it is going to be lower than MP. Cb is a moment correction factor, which is given by this equation, but it is going to be always given to you, and most of the time it is given as 1 in the FE exam. I'm going to explain to you step by step now, and you are going to find that it is actually very simple. I don't want you to get confused because of these equations. You will see that it's going to be a very simple problem in the exam. This is the Zx table. As you can see, we have different shapes, any beam sections, and we have the Zx value, we have the MP, we have the MR, and the LP, the LR, all of these values which we have discussed in the earlier equation here. And this is very important term, that MR x equals 0.7 F yield multiplied by Sx, which is this term here, which means that this term is actually MR, so it is MP minus MR, and BF equals MPx minus MRx over LR minus LP. This in case it was requested for you, this is the beam factor in the problem. All of what we have discussed earlier is called the tables and the equations method. But as we have learned in the columns design also, there is a very simple way to design the beams, which is using the graphs. In using the graphs, you are just going to use the unbraced length for the beam, and it is going to give you directly the available strength or the available moment for this specific beam. Of course, this is way simpler, but again, I wanted to explain to you first the equations and the tables, and we are going to solve the examples using both methods, so whatever method you want to use in the exam, you will be able to use it. So now to summarize our lecture, we have here this table, which is table 3.2. This is selection by Zx. You need only the section name, and based on this section name, you are going to get the MRx, MPx, LP, LR, and the BF. And the second method, which is using this graph 3.10, which is available moment versus unbraced length. And you need here the unbraced length and the section name, and you are going to get directly the phi Mn. So now let's have our first example of this. Here we have a W21-48 beam of A99-2 steel, has a compression flange braced at 6 feet intervals. Assume the beam is compact. What is most nearly the available plastic moment capacity of this beam? Here it is mentioned that this beam is compact, and we want to calculate the available plastic moment capacity of this beam. So we want to start first by obtaining the Zx from the table. This is at our Zx table. So we will go down till we find our W21-48 beam, and in front of it you can get the Zx, which is 107, and the strength of the beam could be calculated by the equation phi Mn equals phi F yield multiplied by Zx, or you can simply find here directly the plastic moment, which is 398 kb/feet, so you don't even have to use any single equation. So simply are going to say that from the table Zx, the phi MP equals 398 kb/feet. As you can see, this is very simple and very direct. You just need to know which table you need to refer to, and this is using the tables and the equations method. There is another method, as we have discussed, which is using the graphs. We are going to check it now. This is the graph which we need to check, which is the available moment versus the unbraced length. You need to find your section here, which is, here it is. This is W2148, and our unbraced length was 6 feet. So it is the first line here. So let's zoom. This is our beam. Let's keep going up. This is it. And here it is. This is the value. No, sorry, 1 second. This is it, W2148, this solid line. Let's keep going up. Here it is the W2148, and here is the value at the 6 feet. So this is 390, this is 405, and here we have 5 spacings, which means each spacing is 3. So we have 1 spacing, 2 spacing, and 2/3 approximately of spacing. So 3, 6, and 2, which is 8. So the value here is 398 kips feet, which is a value which we have already obtained from the table. So as you can see, we could have solved it using 2 methods, and both methods are very simple. So the answer here is the second option, which is 400 feet kips. As you can see, this is very simple, and you could have solved it in few seconds using both methods actually. But this is in case if you have no lateral torsional buckling and the beam is given as compact. So what if you need to check the lateral torsional buckling? That's what we are going to see in the next example. Here we have a W2455 section with F yield of 50 KSI, is used as simply supported beam with a span of 12 feet to support a uniformly distributed load. Taking CB equals 1, what is most nearly the maximum design flexure capacity of this beam if only the ends of the beam are laterally supported? So now we know the section number, and we know the unbraced length of this section, which is 12 feet. So we need to understand first in which stage are we. Is it the plastic, or the inelastic, or the elastic? In order to know that, we need to obtain the parameters LR and LP. So we are going to refer to this table using the type of the section, which is W2455. So here it is, our table. For the W2455, you can see that the LP equals 4.73 and the LR equals 13.9, and our unbraced length equals 12 inches. So this means that we are in the middle between the LP and the LR, which is the inelastic zone. And in this zone, we need to check the lateral torsional buckling using the equations that we have in the code. We will need, of course, as long as we are not less than the LP, we will need the MPRX, which is 503 kip-foot, and the MRX, which is 299 kip-foot. So let's go back to our problem. So now we know that the unbraced length equals 12 feet. And using the table, we obtain that the LP equals 4.73 feet and the LR equals 13.9 feet. So from the table, we will get the phi MP, which equals 504 feet kips, and the phi MR, which equals 299 feet kips. So now we are just going to use the equation, but we need the design flexure capacity. So we need to multiply by phi, and so we are going to multiply both sides of the equation by phi. So phi Mn equals Cb, which is 1 already, multiplied by phi MP minus phi MP minus 0.7 phi F yield SX, all multiplied by LB minus LP over LR minus LP. But we know that 0.7 F yield SX, this is MR, so the phi multiplied by 0.7 F yield SX is the phi MR actually, which is the 299 feet kips. So this equation is going to be 1 multiplied by 504 minus 504 minus 299, all multiplied by 12 minus 4.73 over 13.9 minus 4.73. This is going to equal 341 feet kips, which is the second answer here, which is 340 feet kips. This is using the equations and using the tables. But we have a very simple method also, as we explained, which is the graphs. Let's check also this method. Here is our graph. We need to find our beam, which is W2455. Here it is, W2455. Let's find which one is it. This is the W2455. So here it is, but we are at 12 feet because this is the unbraced length. So it is here. So we are going to follow this line. Here it is till we hit the W2455, which here at this point. Here, this is between the 330 and the 345. So each spacing is 3. So we have 1 spacing, 2 spacing, 3 spacing, and the small portion, the 3 spacing are 9, and the small portion is approximately 1. So the value you can get it from here, which is 340 feet caps, which is the value which we have already calculated using the equations. So you can see that this graph actually is very simple, and you get it directly straightforward using only one step. But of course, this is limited to F yield of 50 KSI and phi of 0.9, which is going to be given to you unless it is a very rare case which these values are not given to you. You will need to have the other method, which is the equations and the tables. That's why I have explained both to you. So this is it for our video today. See you in our next video. Thank you.